During this session I'm going to be explaining about how we can do calculations about circuits when we have an alternating current. So really I'm asking the question, how do we measure the size of an alternating potential difference or current when its value changes from one instance to the next? Okay, so how do we overcome this problem? So let me explain what scientists did. They set up a situation where they had two light bulbs. Each light bulb has exactly the same brightness, exactly the same resistance, so therefore it's giving out exactly the same amount of energy. One of them is set to a 3-volt battery, so there's a direct current and there's always going to be 3 volts across there. The other light bulb is attached to a variable alternating current, so that means that the current is changing all the time. Now if I look at both of these graphically, what I can see is that the direct current trace is always exactly the same, whilst the alternating current goes up and down as we expected. Now if we look closely, the direct current happens to be about 70% of the peak value of the alternating trace, and this is where this term RMS, root mean square value, comes from. So let me explain why this has been chosen. So clearly it's been chosen because this RMS value is equivalent to a steady direct current. We can see that they're giving out the same brightness on that light bulb, so there's an equivalence there. Now the RMS value is about 70% of the peak value, and that happens to be 1 divided by root 2. Okay, so that root 2 is that root element of the peak value. And this is sometimes known as the effective value. Okay, so what we're saying here is that 1 divided by root 2 of the peak value gives us a sensible value for either current or voltage. So the RMS value is equal to the peak value divided by root 2, or vice versa, the peak value equals root 2 times the RMS value. Let's think about power now. So I've identified current, identified voltage, and we'll extend this to power. Now the power dissipated in a lamp varies as the PD across it and the current passing through it alternate. We know that. They're in phase, so power is going to be current times PD, and if we multiply the values of current and voltage at any instant, we can show this graphically. Okay, so here's a graphical interpretation of power. And as we can see here, if we look at current and PD, what happens, the power curve follows exactly the same. It's in phase with current and voltage. And the interesting thing here is that if we multiply the current times the voltage at any moment in time, okay, that means that the maximum power is going to be the peak current multiplied by the peak voltage, and the average is actually going to be half of that. So it's going to be the peak current times the peak voltage divided by 2. Okay, so that's the mean of this calculation. It's where the mean comes from in the root mean square feature. Okay, so this is interesting enough. So we look at a little bit more detail. We can see that the power varies between the peak current times the peak voltage and 0. The average power is therefore half of this. So therefore the power at any moment in time, or the average power, is going to be equal to the peak current divided by root 2 times the peak voltage divided by root 2, or the power is going to be equal to the RMS value for current multiplied by the RMS value for voltage. So all these things come together. So we're given these values, or these formulas, in the IB formula sheet. Okay, so just to highlight here, I said earlier the peak value, and it could be for current or voltage, divided by root 2 gives me the root mean squared value. So that's for current and voltage. The resistance in either situation means that we have to be consistent. Okay, so the voltage peak divided by the current peak is going to be equal to the voltage root mean squared divided by the current root mean squared. So as long as you're using the similar value for voltage and current, you can continue to use the idea of Ohm's law to calculate resistance, which doesn't change. Okay. For power, the maximum power is always going to be the peak current times the peak voltage, and the average power, which we'd more typically get, is going to be half of that value. So some useful formulas to come away from that are to recognize that Ohm's law is V equals IR is consistent as long as we're consistent with using root mean squared and root mean squared. The power can be calculated from the root mean squared multiplied by the root mean squared, and that's the average power we're going to get. The power could also be calculated from the root mean squared current squared and multiplied by the resistance, or the root mean squared voltage squared divided by the resistance. And with those formulas safely in your hands, you should be able to make any circuit calculations you need.